Good day, friends, and you are again welcome to another Wase online experience. My name is Philip, and I'll be your instructor for today. But before we start our activity for the day, I'll need you to subscribe to our channel if you've not already done that. Remember, once new videos are created, you'll be sent an alert if you have subscribed to this channel. To be able to do this, you simply need to go below the video and tap the subscribe button. Alright, thank you very much for doing this for us. Let's look at our activity for the day. We will continue with bearings and vectors. Today we'll be looking at part 8 of this topic. Under this part, we'll be looking at two main things. One, will be looking at the position vector dividing a line segment into a given ratio. Then number 2, we'll be looking at the vector in relation to the parallelogram. I believe you are ready for this. So let's start our activity for the day. We will start by looking at the position vector dividing a line segment into a given ratio. Now let's draw the line segment AB. Let's also show the point T, which divides the line segment AB into the ratios m:n. Now, as we already know, the position vector of the point A will be the vector OA. The position vector of the point T would be the vector OT, and the position vector of the point B would be the vector OB. When the point T divides the line segment AB into the ratios mn, then the position vector of the point T would be given as. So we have the position vector OT, and it is equals to, then we'll take the first ratio m, then we'll multiply it by the vector OB. In other words, we'll multiply it by the vector on the extreme right side of the ratio m. We then take our plus sign, then we write our ratio n. We multiply it by the position vector OA, which is the position vector on the extreme left side of the line segment. We then divide the whole expression by the sum of ratios m and n. So we add the ratio m to the ratio n. So whenever a line segment is divided into a ratio, in this case the ratio m is to n, this is the formula we are going to use to arrive at the position vector of the point that divides the line segment into those two ratios. So in this case, the point is the point T, and its position vector will be, first you take the first ratio, you multiply it by the extreme point on the right side of the line, then you add this to the second ratio, you multiply it by the point on the extreme left side of the line, then you divide the whole expression by the sum of the two ratios. It's as simple as that. Now let's look at an example. Let's assume that the point T divides the line segment AB into the ratios 2:3. Let's also assume that the position vector OA of the point A is 2, 3, and the position vector OB of the point B is 1, 4. So using the following information, let's look for the position vector OT of the point T, which divides the line segment AB into the ratio 2:3. So our position vector OT is equals to the first ratio 2 multiplied by the position vector OB, which is 1, 4. Remember, this is the vector on the extreme right side of the ratio 2. We then show our plus sign. Then we write our second ratio, that's the ratio 3. This will be multiplied to the vector OA, which is 2, 3. And remember, it is the vector on the extreme left side of the ratio 3. Now the entire expression divided by the sum of the two ratios. So we have 2 plus 3. At this point, we would apply simple arithmetics to arrive at our final answer, the vector OT. So our vector OT will be equals to the vector 2, 8 plus the vector 6, 9. Remember, we got the 2, 8 by multiplying the 2 to the vector 1, 8, 4. And we got the vector 6, 9 by multiplying the vector 2, 3 to the scalar 3. So that's how come we arrive at those two vectors. So all divided by the sum of the two ratios, 2 plus 3, that is 5. So our vector OT will be equals to the vector 8, 17 divided by the scalar 5. We got the 8, 17 by adding the two vectors, vector 2, 8 to the vector 6, 9. That's how come we got the vector 8, 17. Let's note that. So at this point, we will divide our vector 8, 17 by the scalar 5. We already know how to do this. When we do this, we would get the vector 8 over 5, 17 over 5. So that is our final answer. The position vector OT is equals to 8 over 5, 17 over 5. And if you are asked to write this as a point T, I believe you know how to write this. It will simply be 8 over 5, 17 over 5. It's as simple as that. Let's look at a few examples. Example 1. Find the coordinates of the point N, which divides the line segment that joins the point A with coordinates 2, 5 and B with coordinate 4, 5 in the ratio 1:2. So first, let's draw the line segment that joins the point A and B. Next, let's show the point N that divides the line segment A and B into the ratio 1:2. So let's show this on the line segment. Now I believe we know that the position vector of the point A is the vector OA. The position vector of the point N is the vector ON, and the position vector of the point B is the vector OB. Also, if the point A is 2, 5, its position vector will be 2, 5. And if the point B is 4, 5, its position vector will be 4, 5. Now let's look for the position vector ON of the point N, which divides the line segment AB into the ratios 1:2. So the position vector ON will be equals to, we'll take the first ratio, which is the ratio 1, multiplied by the vector OB, which is the vector on the right side of the ratio 1. Now write your addition sign. Then you write your second ratio, which is the ratio 2. This will be multiplied by the vector OA, which is the vector on the extreme left of the ratio 2. We will now divide the entire expression by the sum of the ratios 1 and 2. At this point, if we have to find the position vector ON, all we need to do is to substitute our position vectors OA and OB into the equation. So let's quickly do this. So this will give us the 1, which is the ratio 1, multiplied by the vector OB, which is 4, 5, plus the second ratio 2, multiplied by the vector or position vector OA, which is 2, 5, all divided by 3, the sum of the 1 and 2. Our position vector ON will now be equals to the vector 4, 5 plus the vector 4, 10 divided by our 3. Remember, we got the vector 4, 5 by multiplying 1 to the vector 4, 5, and we got the same thing. And we got the vector 4, 10 by multiplying the scalar 2 to the vector 2, 5. So that's how come we got that. When we solve this, our vector ON will be equals to the vector 8, 15 divided by the scalar 3. And remember that we got the vector 8, 15 by adding the 2 vectors at the numerator side of the fraction. So we added 4, 5 to 4, 10, and that's how come we got 8, 15. When we solve for this, our vector ON will be equals to the vector 8 over 3, 5. So at this point we have been able to find the position vector ON of the point N. But remember, the question did not ask us to find the position vector ON. Rather, the question asked us to find the point N. What it means is that we have to find the point N by converting this vector ON to its coordinate form. When we do this, we'll get the point N to be equals to 8/3, 5. Let's look at example 2. Example 2. Find the coordinates of the point K which divides the line segment that joins the point N, which is 1, 2, and the point V, which is 3, 7, into the ratio 2:3. We will first draw our line segment NV. We will then show the point K which divides the line segment NV into the ratios 2:3. Now we already know that the position vector of the point N is the vector ON. The position vector of the point K is the vector OK, and the position vector of the point V is the vector OV. Also, if the point N is 1, 2, then its position vector ON will be 1, 2. And if the point V is 3, 7, then its position vector OV would be 3, 7. Now let's look for the position vector OK. So this will be equals to the first ratio 2 multiplied by the vector OV, which is the vector on the right side of the ratio 2, plus the second ratio 3 multiplied by the vector or position vector ON, which is the vector on the left side of the ratio 3, all divided by the sum of the two ratios 2 and 3. So at this point we'll just substitute the position vectors ON and OV into the equation to get the position vector OK. So let's quickly do this. When you do this, you would get the ratio 2 times the vector OV, which is 3, 7, plus the ratio 3 times the vector ON, which is 1, 2, all divided by the sum of ratios, which is 2 plus 3, and it gives us 5. This would give us vector 6, 14, plus the vector 3, 6, all divided by 5. And I believe you know how we got the 6, 14. We got that by multiplying 2 to the vector 3, 7. And we got the vector 3, 6 by multiplying the 3 to the vector 1, 2. When you solve for this, you would get the vector 9, 20 divided by 5. When you solve for this, you get the vector OK to be equals to 9 over 5, 4. Remember, the question asked us to find the point K. It did not ask us to find the position vector OK. So we have to convert this answer to its coordinate form. When we do this, we would get the point K to be equals to 9 over 5, 4. Let's look at example 3. Example 3. The point E, F, and G lies on a straight line such that the point F divides the line EG in the ratio 3:7. If the point F is equals to 2, 5 and the point G is equals to 4, 1, find the position vector of the point E. From the question, we are being told that the 3 points E, F, and G lies on a straight line such that the point F divides the line EG. What it means is that we have the line segment EG and the point F is in between them, and it divides those two, the line segment, in the ratio of 3:7. So let's draw the line segment EG. Now the point F is in between the 2 points E and G, and it divides the line segment EG in the ratio of 3:7. Now we know the position vector of E to be the vector OE, the position vector of the point F to be the vector OF, and the position vector of the point G to be the vector OG. From the question, we've been given the point F to be 2, 5. So that means that the position vector OF would be 2, 5. And we've also been given the point G to be 4, 1. So that means that the position vector of G, which is OG, would be 4, 1. In this question, we are finding the position vector of the point E. We are not looking for the point F that divides the line segment into those ratios given to us, but rather we are finding the position vector E. But let's remember that the same formula would apply here. The only difference is that after we state the same formula, we'll just change subjects to look for the vector OE. Then from the vector OE, if we are being asked to find the point E, we'll find the point E. It's as simple as that. So let's state the same formula as if we are looking for the point F. If we were to be finding the position vector OF, it would have been equals to the ratio 3 times the vector OG plus the ratio 7 times the vector OE, all divided by sum of the ratios 3 and 7. When you add the 3 and 7 together, you'd get 10. At this point, we'll be doing cross multiplication. So we'll simply multiply the number 10 to the position vector OF. When we do this, we would get the 10 multiplied by the position vector OF, and this will be equals to 3 multiplied by the position vector OG plus 7 multiplied by the position vector OE. Since we are looking for the vector OE, what it means that we have to make the position vector OE the subject by moving the whole of the 3 times the vector OG to the left side of the equation. When we do this, we would get 10 multiplied by the vector OF minus 3 vector OG. This will be equals to 7 vector OE. Now at this point, all we need to do is to substitute our vectors into the equation. So let's quickly do that. We have our 10 multiplied by our vector OF, which is 2, 5, minus 3 multiplied by the vector OG, which is 4, 1. This will be equals to 7 vector OE. Now the 10 times the vector 2, 5 would give us the vector 20, 50. And the 3 times the vector 4, 1 would also give us the vector 12, 3. So now we have the vector 20, 50 minus the vector 12, 3. When you do this simple calculation, you'd get the vector 8, 47. This means that the vector 8, 47 is equals to 7 of the vector OE. We can rewrite this expression in this way. Our 7 of vector OE is equals to the vector 8, 47. At this point, if we want the position vector OE, all we need to do is to divide through the equation by the number 7. When we do this, our vector OE will be equals to the vector 8, 47 divided by 7. This will be equals to the vector 8 over 7, 47 over 7. Therefore, the position vector of the point E, which is vector OE, is equals to the vector 8 over 7, 47 over 7. Well, I believe this was very interesting for you. We are going to look at vectors in relation to the parallelogram. So let's look at the parallelogram, and we would also look at how vectors relate to them. First, we need to know what the parallelogram is. In junior high school, we were told that the parallelogram is a four-sided figure. In other words, it is a quadrilateral. You are also made to understand that the parallelogram has two pairs of parallel sides. This shape A, B, C, and D is a quadrilateral. Let's assume that the sides AB and CD are parallel. So we'll be using the following arrows to indicate that the sides AB and CD are parallel. Again, we will make the assumption that the sides CA and DB are also parallel. So we will use the following arrows to show that they are parallel. So now this quadrilateral A, B, C, and D has two pairs of parallel sides, and this makes it a parallelogram. With this information in mind, we can come up with various kinds of parallelograms. So first, we have the parallelogram itself, what all of us know to be parallelogram. So that's the first kind of parallelogram. The second kind of a parallelogram is the rectangle. Now, a few of us will be surprised by this statement. However, most of us already know this. But the truth is, a rectangle is also considered to be a parallelogram. Remember, when we were defining a parallelogram, we said that 1, it should be a quadrilateral, and 2, it should have two pairs of parallel sides. A rectangle is a quadrilateral. It also has two pairs of parallel sides, as shown here on the screen. So a rectangle is considered to be a parallelogram. The third kind of parallelogram is the rhombus. And here too, a few of us will be surprised. Majority of us, however, will never be surprised by this, because we know that the rhombus is a quadrilateral, and as shown on the screen, it has two pairs of parallel sides. So a rhombus can be considered as a parallelogram. Finally, we have the square. It is also a kind of a parallelogram. A square is a quadrilateral, and it also has two pairs of parallel sides. So it is considered as a parallelogram. So these are the various kinds of parallelograms you can have. Once you have a quadrilateral, and the quadrilateral has two pairs of parallel sides, it is considered as a parallelogram. As simple as that. Now let's look at the features of a typical parallelogram. The drawing or the four shape figure that we all know to be a parallelogram. Let's look at its features. So we have our parallelogram ABCD. So for this parallelogram, let's look at the following features. When you look at this parallelogram carefully, you realize that it has the side AB, and you have an arrow showing that there is a movement from the point A to the point B. This movement can be considered as a vector. So what it means is that a side AB of the parallelogram can be considered as vector AB. So let's write that vector AB down. This parallelogram also has the side CD, which is opposite to the side AB. And also in this case, the side CD shows the movement from the point C to the point D. And we have an arrow that shows this movement. So the side CD can also be considered a vector. And we can give this vector the name vector CD. So let's write that also down. Now the feature you need to know here is this. Whenever you have a parallelogram, opposite sides are always equal. So in this case, the vector AB is equals to the vector CD. So let's bring an equal sign between the two vectors to show that they are equal. Let's quickly do that. So the first thing you need to note about this parallelogram ABCD is that the vector AB is equals to the vector CD because they are opposite to each other. Now it is very possible for us to rewrite this vector equation in its expanded form. To do this, you simply need to rewrite the individual vectors, here in this case vector AB and vector CD, in their resolved component form. We know how to resolve vectors into their component position vectors. So that's what we are simply going to apply here. Let's write the equal sign that separates the two vectors. So first we would resolve the vector AB into its component position vectors. When we do this, we will get the vector OB minus the vector OA. We would also resolve the vector CD into its component position vectors. When we do this, we would get the vector OD minus the vector OC. So these two vector equations, we have 1 and 2, are the same, and at the appropriate time we'll be making use of them. Let's look at the second feature of this parallelogram. The side CA can also be written as the vector CA. So let's write this down. Again, the side DB also shows the movement from the point D to the point B. So it can also be written as the vector DB. So let's write that down as well. Now, what can we say about the relationship between these two sides of the parallelogram? First, let's note that they are opposite to each other. So if they are opposite to each other and they are parallel to each other, what it means is that they are also equal. So let's write our equal sign in between them to show that they are equal. So the second thing we need to note, or the second feature we need to note about this parallelogram, is that the side CA and DB are also equal. Therefore, they can be equated, or those two vectors can be equated. Again, in this case, we need to note that we can expand this vector expression by resolving the individual vectors into their component position vectors. For us to do this, let's first write the equal sign between the two vectors. When we resolve the vector CA into its component position vectors, we would get vector OA minus vector OC. Also, when we resolve the vector DB into its component position vectors, we would get the vector OB minus the vector OD. In this case too, I'll need us to remember that the vector expressions 3 and 4 are the same. One is an expanded form of the other. Finally, let's note that these features we've just looked at also applies to the other kinds of parallelograms, such as rectangles, squares, and rhombus. Now, let's use the concepts we've just learned to solve some examples. Example 1. For the diagram given, the point A is 1,6, point B is 2,2, point C is 5,4, and point D is K, N. Find the coordinates of the point D. Now, the diagram shows a parallelogram ABCD. We've been given the point ABC, but we've not been given the point D, and we've been asked to find the point D and the components of or the coordinates of the point D. That's the S component, which is K, and the Y component, which is N. We've been asked to find them. Now, so we will use whatever we've learned in the previous slide to do this. First, we know that for this parallelogram, the side CD is equal to the side AB. So what it means that a vector CD should be equal to the vector AB. So let's take that information down. Next, let's write this vector equation in its expanded form. In its expanded form, the vector CD will be equal to OD minus OC. Then we would write our equal sign. The vector AB will now be OB minus OA. Very simple, isn't it? At this point, all we need to do is to substitute the information given to us into this expanded vector equation. We know the point A, we know the point B, and we know the point C. So we just need to write them in their position vector format, and we will rewrite them into this equation. When you substitute this, our vector OD minus our vector OC, which is 5, 4, will be equals to our vector OB, which is 2, 2, minus our vector OA, which is 1, 6. So that's what we will get. So this would give us our vector OD minus our vector OC, which is 5, 4, equals to the vector 1, negative 4. And remember, we got 1, negative 4 by subtracting the vector 1, 6 from the vector 2, 2. To get the vector OD, we would have to move the vector 5, 4 to the other side of the equation. So that will be left with just the OD. And when it goes there, it will be negative. Sorry, it will be positive. Remember, it is already negative here. Negative 5, 4. So when it goes there, it will be positive 5, 4. So let's quickly do this movement. When we do this, we will get our vector OD to be equals to the vector 1, negative 4, plus or positive the vector 5, 4. When you compute this, you would get the vector 6, 0. When you have 1 plus 5, that will give us 6. And when you have negative 4 plus 4, that would give us 0. So if the position vector OD is equals to 6, 0, what it means is that if we write it in its component form, the D, it will be D equals to 6, 0. This implies that the K component of the point D is 6 and the N component of the point D is 0. Let's look at example 2. Example 2. In this example, we have been given a certain diagram. Again, we are being told that the vector EA is 2, negative 4, and the vector BC is 2, 7. We are then being asked to find the vector DC. To be able to do this, I'll need us to first identify the region from the diagram given to us where we can find the vector DC. So the vector DC is part or forms part of this yellow triangle. In fact, when you observe this yellow triangle carefully, you realize that the vector DC is the base of this yellow triangle. From this yellow region, we can resolve the vector DC into its component vectors. And when we do this, we would get vector DC equals to vector db plus vector bc. The question is, how did we come up with this equation? Remember that when we move from the point D to the point C, this movement can be represented by the vector dc. Now this vector dc, or this movement, can also be done in another way. First, by moving from the point D to the point B, which is the vector db, then again moving from the point B to the point C, which is the vector bc. So that's why the vector dc was equals to first db plus bc. Now, a careful look at the diagram given to us reveals that the section ABDE is a parallelogram. And what we know about parallelograms is that opposite sides are equal. What this means is that the side DB is equals to the side EA. The reason is that they are opposite to each other. So let's put down that statement. So the side DB, or vector DB, is equals to vector EA. Now let's name the first vector equation equation 1. From our equation 1, or our vector equation 1, to be able to find the vector dc, we need to know the vector db, and we also need to know the vector bc. So all we will need to do is to add the two vectors together to get the vector dc. The question gave us the vector bc. However, the question did not give us the vector db. It rather gave us the vector ea. Now, since we know that the vector db is the same as the vector ea, what we can do is to rewrite the equation 1, but this time around replacing the vector db by the vector ea, since db and ea are the same. So that's what we are going to do. We are going to replace the vector db by its equivalent vector, which is ea. Nothing would happen to the equation. So let's quickly do that. So our new equation, which will be replacing the first equation, will be the vector dc equals to the vector ea. Remember, ea is the same as db, plus the vector bc. At this point, we know the vector ea, we also know the vector bc. So let's just substitute them into the equation to find our vector dc. When we do this, our vector dc will be equals to the vector ea, which is 2, -4, plus the vector bc, which is 2, 7. When we add these two vectors together, our vector dc will be equals to 4, 3. Remember, the 2 plus 2 would give us 4, and the -4 plus 7 would give us 3. Let's look at example 3. Example 3. For the diagram below, the vector EF is 3, 4. The point G is 8, 1. Find A, the point H. Then B, find the magnitude of the vector GH. First, the diagram given to us is a parallelogram. And from what we know about parallelograms, opposite sides are equal. So what this means is that the vector GH is equals to the vector EF. The reason is that they are opposite to each other. So let's first write that statement. So the vector GH is equals to the vector EF. From the question given to us, we know the vector EF. So we do not need to expand or to resolve the vector EF into its component form. The vector GH, on the other hand, we do not know. So we have to write it or resolve it into its component position vectors. When we do this, we would get the vector OH minus the vector OG equals to the vector EF. Remember, the GH was resolved into OH minus OG. So at this moment, we will simply substitute the vectors into the equation to find the vector OH. When we do this, our vector OH minus our vector OG, which is 8, 1, will be equals to our vector EF, which is 3, 4. Since we are looking for the vector OH, what it means that we have to move the vector 8, 1 to the right side of the equation so that the vector OH would stand alone. Remember, the vector 8, 1 has negative in front of it. So when it moves to the right side of the equation, that negative will be positive. So when we do this movement, we are going to get the vector OH equals to the vector 3, 4 plus the vector 8, 1. When we add the two vectors 3, 4 and 8, 1 together, you would get the vector 11, 5. Remember, the 3 plus the 8 would give us 11, and the 4 plus the 1 would give us 5. So the position vector OH will be equals to 11, 5. We can rewrite this in component form, which is the point H, and that is what we are being asked to find. So the point H will be equals to 11, 5. Let's look at the second part of the question. The second part of the question is asking us to find the magnitude of the vector GH. How do we do this? To be able to do this, we first need to find the vector GH. The vector GH will be equals to the vector OH minus the vector OG. This will be equals to the vector 11, 5. Remember, 11, 5 is the vector H or OH minus the vector 8, 1. The vector 8, 1 is the vector OG. When you subtract the vector 8, 1 from the vector 11, 5, you would get the vector 3, 4. So our vector GH is equal to 3, 4. Now let's look for the magnitude of the vector GH. the magnitude of the vector GH will be equals to square root, all into bracket, the x component of the vector GH, which is 3 square, plus the y component of the vector GH, which is 4 squared, bracket closed. When you solve what is inside the bracket, you get 25. So therefore we would get square root of 25. Square root of 25 would give us 5. This means that the magnitude of the vector GH is equals to 5 units. I believe you found this interesting and easy. Well, friends, this brings us to the end of part 8 of bearings and vectors, and for that matter, the entire topic bearings and vectors. In our next meeting, we would look at an entirely new topic, which is algebraic expressions. Until we meet again, I'll need you to stay safe. And please, if you've not subscribed for our channel, kindly do so. We need your subscription for the continuation of this program. Thank you very much.